Welcome to two-dimension separation of variables. So, what we're going to be doing today is to, let me turn this one off. There we go. Really welcome to two-dimension separation of variables. We're going to look at the example that we looked at in class. This was the example of a long rectangular pipe. So it went back in the z direction like this, and also forward. Right, it's just a cross section. And it ranged between negative a over 2 and a over 2 in the y and, x directions. The left and right-handed sides, left and right, are grounded. And the bottom is going to be at positive v naught, and the negative side, the top side will be at negative v naught. So I'm going to write v of x, y is equal to some function x of little x times some function capital Y, which is a function of little y. Now, I know that v does not depend on z because if I were at a different position in z, the pipe will look the same because it's very, very long. So every z point must be physically equivalent, and so I don't have to worry about it, about the z dependence. What I am going to do is solve Laplace's equation in two dimensions. So I have this v delta v squared, and that's going to be the second partial with respect to x squared plus the second partial with respect to y squared times v, which is going to be capital X, remember some function of x, times some function of y. Now I have assumed that v can be in this form. If v cannot be separable in this form, I can approximate it very, very well as an infinite series of functions that are separable, like this one. So the partial only cares about x dependence. There is no x dependence in y, so that pulls right through beautifully, times the derivative of capital X with respect to little x. These are now regular derivatives because x is a function only of one variable. So the partial and total derivatives are the same. And the same thing with the second term. X comes through, does not depend on y, and I just am left with a derivative with respect to y. This is 0. Now what I am going to do is multiply both sides of the equation by 1 over capital X, capital Y. And this here will give me 1 over x times the second derivative of x with respect to the variable little x, plus 1 over y times the derivative of y with respect to little y. This is going to be 0. So what has happened here is that I now have a part that depends only on x. And this part of the equation depends only on y. So if the value of x changes a little bit, this part needs to stay constant because this part won't change if x changes. So therefore, I can say this must be equal to a constant. I'm going to call this constant, let's call it a. By the same reasoning, the right-hand term must also be constant for changes in y, and this will also be equal to a constant, let's call that constant b. So this lets me write now two equations. The first equation is that 1 over x times the second derivative of x with respect to little x equals a constant a. And the other one is that 1 over y, remember the function y that depends on little y, this must be b. And a plus b was 0. Alright, so choosing which one, a or b, is going to be positive or negative depends on our initial conditions. Let's look back at our picture. Here's our picture. notice that x needs to go from 0 on the left-hand side to 0 on the right-hand side. So it needs to be periodic. So I expect to get a sine or cosine, some sort of periodic term. So that means that that particular constant needs to be negative. I'm going to say let a be negative, and specifically I'm going to write it as a equals minus omega squared. B is equal to negative a, so this must be plus omega squared. So now I can write this as the second derivative of some function of x with respect to little x is equal to minus omega squared times that same function. And my y equation is going to be the second derivative of some function of little y with respect to little y squared is equal to plus omega squared times capital Y, which is a function of little y. Now I can solve this x equation. This is just sines and cosines. Capital X is going to be some constant d times the cosine of omega x plus some constant f times sine omega x. Now if I look back at my original picture here, notice that I'm going to go from 0 to 0 on the other side. I'm going to expect an even function. I expect there to be, that doesn't depend on which side of x I'm on, of the origin, or the y-axis, this looks the same. So I expect my odd functions here to be 0. Now if I solve this y equation here, capital Y of y, this is going to be either be equal to exponentials or equivalently to the hyperbolic sine and cosine. When I have conditions like the one here, where I go from negative a value to positive a value, it is much, much easier to use hyperbolic sines and cosines. Exponentials are much better if you go off to infinity. You can talk about long-term behaviors. So I am going to write this as g times the cosh of omega x plus h times the sinh of omega x. Bring this over to the right so we can all see everything. Now again, I know that my y value is going to go from negative to a positive, so it has to go through 0. And that makes this left-hand side impossible because the cosine does not go through 0. The cosh doesn't go through 0. It goes down and it reaches the value here. And this value is 1, while the other axis is down here. So it would be a cosh. All right. Let's put these together and write v of x, y, which was a combination of these two multiplied together. Some constant, obviously d times h, is going to be the cosine omega x times the sinh omega x. This is the general form. It's now time to apply boundary conditions. I say, remember, a over 2, x equals a over 2, some function of y, this better be 0. So this means that c times the cosine omega x times the sinh of omega x. Sorry, omega y. I messed that up earlier, didn't I? So sorry. This x is a over 2. So this means that the cosine of omega a over 2 is equal to 0. When does that happen? That happens at some value n times pi over 2, where n is an odd integer. 1, 3, 5, so forth. And so omega is n pi over a. This allows me to write v of xy is equal to c times the cosine of omega, which I know is n pi over a times x, times the sinh, this also depends on omega, which I now know, n pi y over a. And remember that I said that all functions could be approximated by an infinite series. So I say that really this is an infinite series over all the odd values of n, Cn cosine of n pi x over a times the sinh of n pi y over a. All right, let's use our next boundary condition. And this is going to be the boundary condition at y equals a over 2. So v of x a over 2, which is equal to minus v naught, that was the potential of the top face, is equal to the sum over all the odd values of n, Cn times the cosine of n pi x over a times the sinh of n pi, and now we plug our value in for y, a over 2, over a. This gives me minus v naught is equal to some constant, which is Cn times the sinh of n pi over 2 times cosine n pi x over a. I will now use something known as Fourier Strick. I am going to multiply both sides by the cosine of k pi x over a. And then I will integrate from negative a to a. So what I am going to do is define this nice, I'm going to call this v of x at a over 2. I know it's negative v naught from negative a over 2 to positive a over 2. But in order to get a periodic function, I'm going to have this go to 0 between a over 2 and 3a over 2. It will go back down. Giving me a nice periodic function. And so I can use Fourier Strick. Alright, so on the left-hand side, I get minus v naught. This gives me the integral of the cosine, which is just the sine function k pi x over a over k pi over a, evaluated from negative a over 2 to positive a over 2, because between negative a and negative a over 2, v is just 0. Then I get the integral from negative a over 2 to positive a over 2, and then more zeros. And this will be the integral over all odd values of n. All of the constants just come right out of the integral, which is very convenient. And now I have the integral from minus a to a. Oh, I'm sorry. Just noticed that you all can't see. It's just a small problem. My apologies. The cosine of n pi x over a times the cosine of k pi x over a dx. Now, this guy, if you look this up, you will learn that this is a times the Kronecker delta nk. The Kronecker delta nk is equal to 1 if n equals k, and 0 if it doesn't equal k, which is very powerful. We say that these cosine functions are orthogonal because if they're the same, they act like they're pointing in the same direction, otherwise they act like they're perpendicular. All right, let's rewrite things. Whoops. Guess they wanted to stay together, didn't they? Huh. Okay. I now have minus v naught times a over k pi times the sine of k pi over 2 minus the sine of minus k pi over 2. This is equal to the sum of all the odd values of n, Cn times the sinh of n pi over 2 times a Kronecker delta. Whew. Now notice that all of these terms will be 0 because of this delta function, unless n equals k. So this will give me a whole bunch of 0 plus 0 plus 0 until I get to that one special value where n equals k, and I get ck times the sinh of k pi over 2 times a. On the left-hand side, I get minus v naught times a over k pi. This will give me minus, because it's an odd function, so this gives me 2 times the sine of k pi over 2. So what is this k pi over 2? I know k has to be odd, so if k is equal to 1, then the sine of k pi over 2 is plus 1. If k is 3, then the sine of 3 pi over 2, that's minus 1. If k is 5, I get plus 1, 7, minus 1, and so forth. I can write all of this as minus 1 to the k minus 1 divided by 2. All right. Now, we're making good progress. Oops, so sorry. I'm going to now write this as ck is minus 2 v naught a minus 1 to the k minus 1 over 2 over k pi times the sinh of k pi over 2. Oops, there's an a here, so these a's cancel, which is very convenient. I can treat as this is a minus 1 to the 2 over 2, because that's 1. And I can end up writing this as minus 1 to the k plus 1 over 2 times 2 v naught over k pi times the sinh of k pi over 2, which is very convenient. All right, let's keep going here. This works very nice. I have forgotten one thing to multiply through by, and that is, I also need to do Fourier Strick, but I'm going to multiply by 1. So this is going to give me minus v naught dx. I'm going to integrate from minus a over 2 to a over 2. And remember, that was the integral over all the odd values of n. We're going to integrate this from minus a to a, because remember we had the 0 from negative a to negative a over 2, and then again from a over 2 to positive a over 2, times the cn's times the sinh n pi over 2, and this was the cosine of n pi over a dx. This just gives me minus v naught right here, dx, right? And this just gives me a whole bunch of, times a. And this just gives me a whole bunch of extra, really not so useful information, except if n is 0, in which case this would just be 1, and I'll end up just having a constant. So this really acts like a C naught. Don't worry about the constant value there. And that is because you could have a situation where the value is just constant. That makes perfect sense. That's also even, in its function. Of course, it's also perfectly odd. Well, no, it's just even. Just even. So we need to consider that situation as well. So this gives us v of xy is now equal to negative v naught a plus the sum over all odd values of n of minus 1 to the n plus 1 over 2 to v naught over n pi times the sec of n pi over 2 times the cosine of n pi x over a. I did forget that x over there. Again, apologies. Times the sec of n pi y over a. And this is truly our final answer. Phew! Good job. All right, I will post a link so that we can also see some graphs of how this looks with various terms. Thank you for watching.